Okay, question number 5 is about riding bikes. And you know me, I love a good old bike ride, tandem bike ride, whatever it is. We got Brandon and Chloe, and part A is asking about how many miles did Chloe travel. They gave us a table with Brandon's velocity. So this is Brandon's velocity. And then they gave us Chloe's velocity in these functions. And they asked how many miles did Chloe travel from time 0 to time t equals 2. So we're going to use this upper function because that's the interval that this function corresponds with. But if they gave us a velocity, if they gave us a velocity and we want how many or the quantity, we have to integrate velocity in order to get her miles traveled, okay? So again, her c of t is actually velocity. So when you integrate c of t, that's going to go ahead and get your distance traveled and how many miles she went. So I'm going to go ahead and integrate from 0 to 2 her function, which is t e to the 4 minus t squared dt. And this antiderivative looks pretty complicated to me. So I'm going to go ahead and do u substitution. I'm going to make my u 4 minus t squared. Therefore, the derivative of u with respect to t would be negative 2t. When I separate my variables, I would get du equals negative 2t dt. Now notice I need a t dt when I go to rewrite my integral with respect to time. With respect to u. And I do not have a t dt. I've got an extra negative 2. So I'm going to divide that out. So I'd get negative 1/2 du equals t dt. So when I go to rewrite my integral, instead of writing t dt, I'm going to rewrite negative 1/2 du. And I'm going to put my negative 1/2 constant out front and du here. I will be left with what I still need to compensate for within my original integral is e to this quantity. But notice this quantity is what we made u. So I'm going to say I've got the integral of e to the u du multiplied by the constant of negative 1/2. We can take that antiderivative, but first we should put our bounds. We should rewrite our bounds with respect to u. So these bounds are meant to be plugged into a t. So I'm going to say, all right, well, what would u of my upper bound of 2 and what would u of my lower bound of 0 be if I plugged them into my t? So 4 minus 2 squared would be 0. 4 minus 0 squared would be 4. So my upper bound was 2, it's going to be 0. My lower bound was 0, it's going to be 4. Now, some people might be tempted to say, I want to flip my bounds. And what that would do is it would get rid of the negative sign in front of my integral. That's totally fine. You don't have to, but you're welcome to. I'm going to go ahead and use this flipped bound method. The antiderivative then of e to the u is e to the u, and I have my 1/2 out front. I'm going to integrate that from 0 to 4. Again, I'm just going to leave my 1/2 out front. I'd have e to the 4th minus e to the 0. We could end there, but that is the same as 1/2 times e to the 4th minus 1, and we are done. In order to know if Chloe's speed is increasing or decreasing, we need to go ahead and take a peek at her velocity as well as acceleration. If her velocity and acceleration have the same sign, then we know that she is speeding up. Meaning if my velocity and my acceleration are both positive or both negative, she's speeding up. If my velocity and acceleration have different signs, one is positive, one is negative, then we know that she is slowing down. So let's go ahead and take a peek at Chloe's velocity. And again, it says at t equals 3 because t is 3 is in this interval between 2 and 4. I'm going to go ahead and use this bottom velocity equation for Chloe. So I'm going to say Chloe, ooh, that is ugly. Chloe, her velocity was 12 minus 3t minus t squared. And I'm going to go ahead and calculate what is that velocity at 3. So this is already a velocity equation. So I'd have 12 minus 3 times 3 minus 3 squared. So I'd have 12 minus 9 minus another 9, and I'm going to get negative 6 is her velocity at 3. Her acceleration would be the derivative of velocity. I'm first going to find it just in terms of not x, but t rather. Her derivative of velocity, the derivative of 12 is 0, the derivative of negative 3t is negative 3, and the derivative of negative t squared is minus 2t. Therefore, her acceleration at 3 would be negative 3 minus 2 times 3. Negative 3 minus 6 gets me a negative 9. Again, I'm not as worried about their quantities as much as their signs, because both my velocity at 3 and my acceleration at 3 were both negative. We know that Chloe's speed was increasing. And my explanation, because I said give a reason, I'd say Chloe's speed is increasing because her velocity and acceleration at t equals 3 are both negative, or you could say at t equals 3 have the same sign. They gave us Brandon's velocities in terms of a table. And in order to go from velocity to acceleration, and I'm going to make sure, did they tell us that Brandon's function is continuous and differentiable? It says Brandon's velocity in miles per hour at time t is given by a differentiable function. Notice that they didn't say differentiable and continuous. And they didn't because that would be slightly redundant. If they're letting you know a function is differentiable, in order for it to have a slope at all points, meaning it is differentiable, it has to be continuous. So because they told us that it is differentiable, therefore we know Brandon's velocity is also continuous. Minutes, I believe, hours. Brandon's velocity was 1.5. Well, Chloe's velocity 2 hours in, we would go ahead and need to use, top function or bottom function, because t could be less than or equal to 2. We're going to use the top function. That was t times e to the 4 minus t. T 4 minus t at her velocity at 2 hours. And, look at 2 here. Should we use the top function or the bottom function? The top function, my t is less than or equal to 2. So we're going to use that top function, which was t e to the 4 minus t squared. Now look at the table. His velocity at 0 hours was 1 mile per hour. All right, they want to know, is there a time on my interval from 0 to 4 at which Brandon's acceleration is equal to 2.5 miles per hour? And they want a justification. Well, if we look, what we would do is find the slope. So from 0 to 4, I could go ahead and find the slope old school style and do y minus y over x minus x. So I'm really doing b of 4 minus b of 0 all over 4 minus 0. Old school slope. The derivative or the slope of velocity gets me acceleration. B of 4 is 11. B of 0 is 1 over 4 minus 0. So I'd get 10 over 4, which is the same as 5 over 2, which is 2.5. Now it says, is there a time where his acceleration is equal to 2.5 miles per hour? Before I even did this, what I just did is I used the mean value theorem. But we can't use the mean value theorem until we're sure that my function, b, is continuous and differentiable. So I'm going to go. So because we know that Brandon's velocities are differentiable, therefore his function is continuous, that's why we can apply the mean value theorem. And the mean value theorem says that the average slope, which we just found over the interval, there will be at least one time that the function, his acceleration, will be equal to the average slope of his velocity. So my justification is going to say, because b of t is differentiable, and continuous, and I know that sounds a little redundant, but that's okay. The mean value theorem can be applied, and There is a time on the interval 0 to 4 where Brandon's acceleration equals 2.5 miles per hour per hour. Okay, is there a time at which Brandon's velocity is equal to Chloe's velocity on the interval from 0 to 2? All right, so let's go first look at Brandon's velocity at 2. Let's go ahead and see at 2. So I'm going to go ahead and say, all right, b of 2 is 1.5. And what was Chloe's velocity at 2 hours in? Well, we need to be e to the 4 minus t squared. So c of t was t e 4 minus t squared. So if I'm trying to do c of 2, I'm going to have 2e to the 4 minus 2 squared, which would be 2e to the 0, which is 1. So Chloe's velocity 2 hours in was 2. Brandon's velocity 2 hours in was 1.5. Let's go find their velocities at 0. Brandon's velocity at 0, so that gets us 1 mile an hour. Chloe's velocity at 0 hours, if I plug in 0 to my function, I'd get 0 e to the 4 minus 0, which we know is 0. So Chloe's velocity at 0 hours was 0, and Brandon's velocity at 0 hours was 1. So what we want to think about is, was their velocity ever equal to one another? This is going back to the intermediate value theorem again. So do you agree that Brandon's initial velocity, which was 1, and Chloe's initial velocity, that was 0, if I take his initial velocity minus her initial velocity, we'd get 1 minus 0, which is 1, which is a positive number. Then if we take his ending velocity at 2 minus Chloe's ending velocity at 2, we'd have 1.5 minus 2, which is negative half. And a negative number is less than 0. And the intermediate value theorem says if the change in their velocities went from a positive number to a negative number, in order to get from a positive number to a negative number, do you agree you have to go through 0? To get from any positive to a negative, we have to go through 0. So at some point, b of t minus c of t had to be equal to 0. And if that's the case, I could add c of t to both sides and I'd get b of t equals c of t. And that's what they asked. Is there a time where Brandon's velocity equaled Chloe's velocity? And we would say yes. And we'd say because the intermediate value theorem, there is a time on the interval 0 is less than t is less than 2 when b of t equals c of t. And to get that point, AP needs to see either this statement or this statement with the intermediate value theorem words or letters.